By the end of this video, you should be able to hand calculate reaction temperature in x-mole fractions of products of gas-gas reactions that are seen in combustion reactions, such as those that occur in rocket engines and jet engines and internal combustion engines. These same chemical reactions could be calculated by a computer in many available chemical kinetics programs, such as NASA's Chem003c. My purpose in making this video is to show you the calculations that go on within these chemical kinetics programs. I'm not going to sugarcoat this. The material is dry and a bit of a slog to get through. If you're not interested in how chemical kinetics work at the most basic level, you may skip this video and move on to the next video in my chemistry series. As a prerequisite for discussing what happens in real chemical reactions, we must discuss chemical equilibrium in gas-gas reactions. Recall the simple equation for forming water. H2 plus 1/2 O2 forms H2O. This simplified equation has the form shown. The small letters indicate mole fractions. The capital letters indicate species. In the case of the water reaction, A equals 1, capital A equals H2, B equals 1/2, capital B equals O2, C equals 1, capital C equals H2O, and that these are not relevant. For the relevant species, the chemical equilibrium constant, Kp, has the forms shown. Inside the brackets, we would enter the partial pressure of each chemical species. As the partial pressures add up to the full pressure, we would be able to determine the x-mole fractions from the partial pressures of each of the species. Mole fraction and partial pressure are proportional. The contribution of each gas species' partial pressure to the total pressure is the same as that species' x-mole fraction to the total number of moles. Observe the equations shown. The total pressure is the sum of partial pressures. The total moles is the sum of moles of each species. The partial pressure of species A equals the mole fraction of species A times the total pressure. Therefore, the mole fraction of A equals the partial pressure of A divided by the total pressure. And these relations between partial pressure and mole fraction apply to the rest of the species. So, if we know the total pressure, and we can find the partial pressure contributed by each gas species, then we would know the x-mole fraction contributed by each gas species. Chemical equilibrium is discussed in depth on the YouTube channel De Novo Tutor at the link I post below. I gained my own knowledge of chemical equilibrium from UC San Diego professor Stanford Penner's book, Chemistry Problems in Jet Propulsion. And I borrow Penner's equilibrium tables, which he in turn borrowed from the National Bureau of Standards MBS Circular 500. Chemical equilibrium tables will help us get the x-mole fraction of each chemical species at a predicted temperature. All this material I'm about to go over can be handled by software programs such as Chemkin or NASA's CEA Chemical Equilibrium application developed by Dr. Bonnie McBride. I just want to give you an understanding of the math behind the software. If you don't want it or need it or it makes your eyes glaze over, you can skip ahead. Many chemical processes happen at a fixed pressure. The pressure in the combustion chambers of a car engine, a reciprocating internal combustion engine, is set by the compression ratio. From the highest pre-ignition pressure of the air-fuel mix, the pressure of the cylinder chamber will rise once combustion starts. In the combustion chamber of a rocket engine, the chamber pressure will be fixed at a constant pressure by the capabilities of the fuel pumps and oxidizer pumps. The chamber pressure will not rise above the maximum exit pressure of the propellant pumps. Any higher chamber pressure than the pump pressure would result in reverse flow. The pumping would stall until the chamber pressure fell back to the maximum pump exit pressure. And so the pressure in a rocket engine chamber is fixed by the propellant pump maximum exit pressure. When substances react, they do not necessarily react completely. In a rocket's exhaust, no matter how efficient the combustion, there will always be some unburnt fuel, some unused oxidizer, and some secondary reaction products besides the main products expected. Even within what we call a pure quantity, such as a vessel containing pure hydrogen gas H2, there will always be free uncombined hydrogen atoms. The ratio of combined hydrogen molecules H2 to free hydrogen atoms H is dependent on the temperature and pressure. If you change the temperature and pressure within the vessel, the ratio of combined hydrogen molecules H2 to free hydrogen atoms H will change until the equilibrium ratio for the new temperature and pressure is reached. Experiments have been conducted at various temperatures and pressures to find the equilibrium ratios at which many different substances exist with each other. Tables of the equilibrium ratios of some common exhaust products are found in S.S. Pinner's book or the MBS Circular 500. In the tables, Kp2 gives the equilibrium ratios dependent on pressure of free hydrogen H to hydrogen gas H2 at various temperatures. pH is the partial pressure of atomic hydrogen. pH2 is the partial pressure of diatomic hydrogen gas. If the vessel contains just H2 and H, the total pressure is the sum of the partial pressures. I give an example for calculating mole fractions with a known temperature and pressure. At 1000 degrees Kelvin, Kp2 is 2.2693 times 10 to the negative 9. If at 1000 Kelvin, in the pressure of 3 atmospheres, a vessel is known to contain 6 times 10 to the 23 hydrogen gas molecules, how many free hydrogen atoms must it also contain? We can do the math by plugging in the correct values for the Kp2 ratio. Rearranging to solve for H gives us 994 H atoms. We see that at 1000 degrees Kelvin, the number of free hydrogen atoms to hydrogen gas molecules is almost insignificant. At 3500 degrees Kelvin, Kp2 is 5.8993 times 10 to the negative 1. If at 3500 degrees Kelvin, in a pressure of 3 atmosphere, a vessel is known to contain 6 times 10 to the 23 hydrogen gas molecules, how many free hydrogen atoms must it also contain? We do a little algebra to solve for H, and we find the number of H atoms is 2.58 times 10 to the 11th. At still higher temperatures, the number of free hydrogen atoms in the vessel may exceed the number of hydrogen gas molecules in the vessel. At very high temperatures, the collisions between the particles will become so violent that all or almost all of the molecular hydrogen will dissociate into individual hydrogen atoms. We can look at another example of calculating mole fractions from a known temperature and pressure. In this example, we will find the chemical equilibrium of oxygen. A vessel contains 1 mole of oxygen at a temperature of 2750 Kelvin and a pressure of 5 atmospheres. We will use the equilibrium tables to find the moles of oxygen gas, O2, and the moles of free oxygen atoms, O, present in the vessel. We should also find the molecular weight and the total weight of gas in the vessel. First, we know the number of oxygen atoms, O, plus molecular oxygen, O2, equals 1 mole. We can say that M equals 1 mole. To find the ratio of free oxygen O to molecular oxygen O2, we use the Kp1 column. We can arrange the Kp1 formula to solve for O. We know that M equals O2 plus O. We can rewrite M in terms of just O2. We can rearrange to set the whole equation equal to 0. At 2750 Kelvin, Kp1 equals 4.7424 times 10 to the negative 2. If P equals 5 and M equals 1, then we can enter these values into the equation. We now have a quadratic equation in the form ax squared plus bx plus c equals 0. X equals square root of O2. And we can solve for this x with the quadratic formula. So the square root of O2 has 2 roots, 0.989 or negative 1.01. The square root of a real number can't be negative, so O2 equals 9.79 moles. We can use this value for O2 to plug back into the formula to solve for O and find that O equals 0.0209 moles. Since we know M equals 1 and M equals O2 plus O, we can apply these values to check our answer. If the molecular weight of O2 is 31.9988 grams per mole and the molecular weight of oxygen O is 15.994 grams per mole. Then we can add these up to find that the mass of the oxygen in the vessel is 31.66 grams. And since we said there was 1 mole of oxygen in the vessel, then the molecular weight of the gas in the vessel is 31.66 grams per mole. The easiest way to learn equilibrium chemistry is by example. This time I'm going to calculate mole fractions from a known pressure and an unknown temperature. This will be an example of how we can use equilibrium tables to find the mole fractions of a much more complicated group of gases in the combustion chamber of a rocket engine. If 1 mole of hydrogen gas were to react completely with 1/2 mole of oxygen gas, the result would be 1 mole of water. Since no real reaction is complete, in a true reaction between 1 mole of hydrogen gas and 1/2 mole of oxygen gas, several products besides H2O would be found in the combustion chamber of a rocket burning these gases. Each x mole of chamber gas will be made up of fractions of mole x of each of these chamber products. If we knew the chamber pressure and the chamber temperature, we could find these mole fractions. If the chamber pressure is 20 atmospheres, what will be the energy released, the chamber temperature, the x mole fractions of H2O, H2, H, O2, O, and OH? So we are given the rocket chamber pressure is 20 atmospheres. This is the propellant pump pressure into the rocket chamber. This pressure is a boundary condition, 20 atmospheres. Many rocket engines are cooled by their propellants. So, the propellants leave the propellant pumps as hot gases. The pressure is fixed by the performance of the propellant pump. We assume the combustion reaction is fast. We assume that time is not a factor. We assume that the reaction is occurring at sufficient distance from the chamber walls that the chamber cooling does not affect the reaction temperature. We assume the reaction occurs in adiabatic conditions. We're going to use an iterative method. We're going to make a guess, find a result, and then make a better guess for the next iteration. For a first guess at solving for the chamber temperature, we can guess a chamber temperature of 3,250 degrees Kelvin. Although molecules and number of molecules change during a chemical reaction, the number of atoms and the measurable weight of the atoms will be the same before and after the chemical reaction. To find the correct values of H2 and O2, we must keep track of all the atoms or moles of atoms during the reaction. If a hydrogen gas molecule contains 2 hydrogen atoms, TMH is the total moles of hydrogen atoms in a given mole of hydrogen gas reactant. TMH equals 2. If an oxygen gas molecule contains 2 oxygen atoms, TMO is the total moles of oxygen atoms in a given half mole of oxygen gas reactant. TMO equals 2 times 1/2 equals 1. The ratio of mix of fuel to oxidizer per atom for this reaction is mix equals TMH over TMO equals 2. Now we must look for the appropriate equilibrium tables that we can use with the combustion products that we will be dealing with. The common denominators in each of the equations is H2 or O2 or combinations of both. The trick is going to be to rewrite the equations to isolate all the combustion products in terms of H2 or O2. We rearrange the Kp1 equation to isolate O. We rearrange the Kp2 equation to isolate H. We rearrange the Kp3 equation to isolate OH. We rearrange the Kp4 equation to isolate H2O. We now have the equations for all the combustion products in terms of H2 and O2. We will now attempt to find the value of O2 in terms of H2. We can make the sum of the mole fractions of all the products equal 1 mole. We can rewrite this summation in terms of H2 and O2. We can rearrange this formula to get the values with square root of O2 in them all together. Subtract 1 from both sides to get an equation equal to 0. We now have a quadratic equation of the form a times x squared plus b times x plus c equals 0. X equals the square root of O2. The value of x in the quadratic equation can be solved with the quadratic formula. A little more manipulation and we now have a formula for O2 in terms of H2. Since we were given the chamber pressure is 20 atmosphere and at 3250 Kelvin, we know the Kp values for any value of H2. We can find the value of O2 and then get the mole fraction for all the other products. The mole fractions can be figured with a pocket calculator, but this is a tedious and time-consuming task. I use a personal computer with a Fortran-like math program to do my calculations. Software programs like MathCAD or MATLAB work well. A spreadsheet program like Excel would probably work well too. When I made the H2 value 0.05, I used the formula to find that O2 equals 0.0111408. Using these values of H2 and O2 in their respective formulas, I found the mole fractions of the other products. When I sum the products, M come out to be 1 mole as expected. Next, I counted the moles of hydrogen atoms by adding up the mole fractions of products which contain hydrogen. Remember to multiply those molecules which contain 2 hydrogen atoms by 2. The sum MH equals 1.6338. Next, I counted the moles of oxygen atoms by adding up the mole fractions of products which contain oxygen. Remember to multiply those molecules which contain 2 oxygen atoms by 2. The sum of the product M0 equals 1.045. If we divide MH by MO, we will get the ratio of hydrogen to oxygen. MH over MO equals 1.5628. This ratio is lower than the mixed ratio, which was TMH over TMO equals 2. This means the value of H2 equals 0.05 is too low. We need to find an H2 value that results in MH over MO equals TMH over TMO equals 2. When I tried H2 equals 0.1, I found O2 equals 0.03 and the rest of the product values. By summing these product values, I found that MH equals 1.825 and MO equals 0.909. Next, we get the ratio of hydrogen to oxygen, MH over MO equals 2.0068. And we find that since this result is slightly higher than our mix equals 2, that our value of H2 is a little too high. At least we now know that our value of H2 should be between 0.05 and 0.1, probably very close to 0.1. After a whole series of trials, I found if I make H2 equals 0.09883, the rest of the numbers work out well. With these values, MH equals 1.823, MO equals 0.9115, and the mix is 2 just like we want it to be. Because TMO over MO equals 1.097 at 3,250 degrees Kelvin, the products of a reaction between 1 mole of H2 and 1/2 mole of O2 equals 1.097 moles of particles. The specific number of molecules of these products can be found by multiplying their mole fraction by values of 1.097 and then multiplying this figure by Avogadro's number 6 times 10 to the 23. We could also say that at 3,250 degrees Kelvin, the reaction of 0.911 moles of hydrogen atoms with 0.455 moles of oxygen atoms results in the creation of 1 mole of products. If we found the energy released in creating these products, we would find our initial guess temperature of 3,250 degrees Kelvin is too low. We will repeat this calculation at 3,500 degrees Kelvin to see if we get better results. First, we must find the mole fractions of products at 3,500 degrees Kelvin. We can reuse the equations for products in terms of H2. We were given the chamber pressure is 20 atmospheres, and we know the Kp values at 3,500 degrees Kelvin. All we have to do is assign H2 values by trial and error until the mix equals 2. After a whole series of trials, I found that if I make H2 equals 0.138, the other products come out nicely. With these values, MH equals 1.712, MO equals 0.856, and the mix is 2 just like we want it to be. Because MO over TMO equals 0.856, we can say at 3,500 degrees Kelvin the reaction of 0.856 moles of hydrogen gas with 0.42 moles of oxygen gas results in 1 mole of products. To find out if 3,500 degrees Kelvin is the correct chamber temperature, we will find the net energy that will result from the dissociation of the original reactants H2 and O2 and the creations of new products H2, O2, H2O, and OH. To dissociate 0.856 moles of H2 into free hydrogen atoms, you must add 89.208 kcals of energy. To dissociate 0.428 moles of O2 into free oxygen atoms, you must add 50.68 kcals of energy. So the energy you must add to dissociate the reactants is 139.89 kcals. Now we find the formation energy of the products. The formation of H2O releases 141.96 kcals. The formation of H2 releases 14.45 kcals. The formation of O2 releases 5.212 kcals. The formation of OH releases 10.32 kcals. If we total up the energy released, we get 171.96 kcals. To get the net energy given off, we subtract the dissociation energy from the energy released. And we find the net energy released is 32.28 kcals. We will find out if this much energy could have boosted the system from its initial reaction temperature of 298 K to a chamber temperature of 3,500 K by finding the enthalpies of reaction of the products at 3,500 K and at 298 K. The differences in enthalpies will be the energy needed to accomplish this task. From the enthalpy tables, the enthalpy of H2O at 298 K is 2,367 calories per mole. The enthalpy of H2O at 3,500 degrees Kelvin is 38,675 calories per mole. If the mole fraction of H2O is 0.64 moles, the energy difference is 23,302 calories. So we can say that 0.64 moles of H2O absorb 23 kcals of heat between 298 K and 3,500 degrees K. We repeat the same process for the rest of the products. The enthalpy of H2 at 298 K is 2,023 calories per mole. The enthalpy of H2 at 3,500 degrees Kelvin is 27,000 calories per mole. We found the mole fraction of H2 was 0.138 moles. So the enthalpy difference for H2 is 3,553 calories. So 0.138 moles of H2 absorb 3.5 kcals of heat between 298 K and 3,500 degrees K. Moving on to free hydrogen, we find that 0.049 moles of H absorb 0.781 kcals of heat between 298 K and 3,500 degrees K. For O2, we find that 0.044 moles of O2 absorb 1.244 kcals of heat between 298 K and 3,500 degrees K. For free oxygen, we find that 0.024 moles of O absorb 0.389 kcals of heat between 298 K and 3,500 degrees K. Finally, for OH, we find that 0.101 moles of OH absorb 2.64 kcals of heat between 298 K and 3,500 degrees K. If we add up all these values, we get the total heat that 1 mole of products can absorb between 298 K and 3,500 degrees K. So we find that 1 mole of products absorb 31.91 kcals of energy in its temperature rise between 298 K to 3,500 degrees K. We already found that the energy released by the creation of the products is 32.2 kcals of heat. So we see that the heat given off is very close to the heat absorbed. This means the chamber temperature must be just above 3,500 degrees Kelvin. To sum up what we did, we started out with the question for the rocket chamber combustion reaction. H2 plus 1/2 O2 gives us so many x moles of products plus energy. If the chamber pressure is 20 atmospheres, what will be 1, the energy released, 2, the chamber temperature, 3, the x mole fractions of H2O, H2, H, O2, O, and OH. We use the chemical equilibrium tables and the enthalpy tables to answer these 3 questions. For answer 1, we found the energy released is 171.97 kilocalories per mole. When we subtract the dissociation energy of 139.68 kilocalories per mole, we get a net of 32.3 kilocalories per mole of product. This 32.3 kcals per mole of net energy would increase the chamber temperature from 298 K to just over 3500 degrees Kelvin. So for answer 2, we found the chamber temperature should be just over 3500 degrees Kelvin. For answer 3, after a whole series of trials, I found that if I make XH2 equals 0.138, then XO2 comes out to be 0.044, and the rest of the products come out as shown in the list. These X mole fractions add up to 1 mole of product from our original equation. Before I conclude this video on gas-gas reactions and the subtopic of hydrogen-fueled rocket engines, I want to let you know that my next video in this chemistry series will be on wet chemistry. Wet chemistry is the study of reactions that occur in water. My starting topics will be solvents and then acids and bases. Back to the subject of hydrogen-fueled rocket engines. The first stage or booster stage of the Saturn V moon rocket, as well as SpaceX's Falcon 9 and Falcon Heavy, all use RP-1 kerosene burned with LOX as their propellants. Lots of other rocket engines use hydrogen H2 burned with LOX, or liquid oxygen, as propellant. The more famous of these hydrogen-fueled rockets include the Space Shuttle's main engines, the upper stages of the Saturn V moon rocket, and the core engines of NASA's Artemis SLS space launch system. Both the Space Shuttle and SLS use Aerojet Rocketdyne RS-25 hydrogen fuel burning engines. On the Space Shuttle, the liquid hydrogen fuel and the LOX are stored in the giant orange fuel tank that both the orbiter and the solid rocket boosters are attached to. The RS-25 fuel-air mix is not the 2 moles of H2 for every 1 mole of O2 as in my example. The RS-25 Space Shuttle main engine fuel mix is more like 6 moles of H2 for every 1 mole of O2. This extra H2 results in excess H2 in the final rocket exhaust. This excess H2 makes the average molecular mass of the exhaust gas leaving the rocket nozzle much lighter than it would be if the rocket gas was predominantly H2O water vapor gas. The lighter the exhaust gas, the higher the exit velocity. H2O gas has a molecular mass of 18 grams per mole. H2 gas has a molecular mass of only 2 grams per mole. The rocket's thrust is essentially the rate of momentum, m.v, of the gas leaving the rocket nozzle. The lighter the exhaust gas, the higher its velocity v will be. So for an equal mass flow rate m dot of rocket exhaust, the lighter the exhaust, the higher the v. So its m dot v thrust will be greater than the heavier exhaust gas with a lower velocity v. And so this is the reason why so much extra H2 fuel is mixed with the LOX in the Space Shuttle RS-25 main engines. Of course, this extra H2 will use up heat energy and reduce the chamber temperature of the rocket engine. But not too much, and on balance, the higher exit velocity of the lighter exhaust gas more than makes up for the reduced chamber temperature. A calculation with 6 moles of H2 for every 1 mole of O2 will result in a lower chamber temperature than the 3500 K we calculated in my example of 2 moles of H2 for every mole of O2, but not too much lower, maybe a chamber temperature more like 3200 degrees Kelvin. Each RS-25 engine produces 418,000 pounds of thrust. The Space Shuttle uses 3 RS-25 engines to give its main engines a combined thrust of 1.25 million pounds of thrust. The SLS uses 4 RS-25 engines to give its core engines a combined thrust of 1.7 million pounds of thrust. In addition to main engines, both the Space Shuttle and the SLS use 2 solid rocket boosters. The SLS's solid rocket boosters are modernized versions of the Space Shuttle's solid rocket boosters. The SLS rocket boosters are 25% more powerful than the Space Shuttle rocket boosters because of an improved propellant mixture. The solid rocket boosters for the Space Shuttle use the solid rocket propellant compound PBAN-APCP. The SLS uses PBAN-APCP plus a powdered aluminum mixture that gives it extra power above and beyond that of the original Space Shuttle rocket booster propellant. PBAN stands for polybutadiene acrylonitrile. The PB or polybutadiene is a synthetic rubber often used to make car tires. The AN is acrylonitrile fuel that has the basic chemical formula C3H3N. APCP is ammonium perchlorate oxidizer. This PBAN fuel is mixed with the ammonium perchlorate oxidizer as a liquid that is poured into the rocket booster casings and allowed to solidify. For the SLS boosters, powdered aluminum is added to the PBAN APCP to give the SLS booster 25% more thrust. Each solid rocket booster provides 3 million pounds of thrust. For the SLS, each solid rocket booster's thrust is increased to 3.7 million pounds of thrust. So the total thrust of the space shuttle, 3 main engines plus 2 solid rocket boosters, is 7.2 million pounds of thrust. The SLS's 4 core main engines plus 2 solid rocket boosters give it a total of 9 million pounds of thrust.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery. A tribute to the dedication, hard work, and pride of America's space shuttle team. The shuttle has cleared the tower.
Discovery. This is Mission Control Houston. The space shuttle now rolling over onto its back for an 8.5-minute ride into orbit. Discovery now making one last reach for the stars. Engines are now throttling down as the orbiter passes through the area of maximum pressure, reducing the stress on the shuttle as it goes supersonic.
Discovery Houston, you are go at throttle up.
Commander Steve Lindsay acknowledging the call from Capcom Charlie Hoba as Discovery's 3 main engines throttle back up. Lindsay is joined on the flight deck by pilot Eric Bowen, mission specialist Al Drew, and Nicole Stott. Mission specialist Mike Barrett and Steve Bowen. Discovery's 3 main engines are burning fuel at a rate that would drain an average swimming pool in about 25 seconds. The engines combined with the solid rocket boosters produce more than 7 million pounds of thrust. 1 minute, 50 seconds into the flight, we're standing by for separation of the twin solid rocket boosters. Discovery now traveling 2,695 miles an hour. Its altitude 24 miles. Downrange from the Kennedy Space Center 29 miles. Booster separation confirmed. Discovery's guidance is now converging as the shuttle's onboard computers fine-tune the flight.
And that concludes my video on gas-gas reactions. Stay tuned for my next video on wet chemistry. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.